just open that link and download it, because the files are very big. A file of in the program that I'm using, nor it can easily go to 50 megaparsecs. Yeah. 50 It's involuntary humor. Okay, so we're going to continue now with the Maple worksheets. Worksheets. And were you able to download your tensor? Yeah. Yes? And so now I also sent the alias file, and what we can also, what you will be required to do now is if you want to follow it with GR Tensor. How many of you have GR Tensor installed? Okay, so it's worthwhile. So we're going to generate the Maple file, the text file. You need to generate a text file and to place it in the directory where well, you downloaded GR Tensor, but did you try it? Yeah. Yes? Were you able to run it? Now what you need to do is to, if you can do this very fast, we'll do it. Otherwise, just follow me. Just follow me, and then later I'll show you how. Because GR Tensor requires the metric files to be in a specific location, and you have to edit the init file, initialization file, so that it will look at the file in the place where it has to be. So, okay. So we already saw this one, so let me try now this one. Can you see? Is it okay? Or want it larger? Let's do it a little bit larger. Okay, so better? Yes. So let me erase this so that you know that. Well, once you have GR Tensor, and then here, this is the file. If you don't have this file, then you won't be able to follow to do it, because what this is doing is to declare the variables. Suppose you have several functions, and the functions have dependence on certain coordinates. This is where you declare it. I'm going to show you to show you very fast this is the one we used yesterday. So the one we're using now is here. This is the one we're going to use. This is a text file that you have to generate. And then the name that you have to put is on top. But see, I don't want to waste time on these details because it's our technical details on the installation and so on. So either in the break or after the lectures today, I'll show you, I'll dedicate that. We can also dedicate the hour after lunch for dealing specifically with these details, okay? Or even if you want afterwards, I'm also willing to sit down and fix all these details of the files and so on and so on. Okay, so because otherwise we will waste 1 hour on doing these things, and I think it's more important to go through the material. Is that okay?
Yes.
Okay, but just to show you, in order to run GR Tensor, well, GR Tensor itself has a bank of this type of files, but always it's good to make your own files. This is a Friedman-Robertson-Walker, the pointer. This type of files in order to operate on them. As you can see, declare the number of dimensions, and here you see the alias. I'm declaring the character capital A to be a function of t. The advantage is that that you are not going to be carrying A of t all the time, A of t. It will only appear A, and the derivatives will not appear as quotients, but simply as A, and then the subindex. The derivatives are given as subindices, you will see it. Then you declare the name of the coordinates, and then you input the metric. As you can see here, I'm not writing A of t, because the alias is already telling Maple that A depends on t, right? So you have to run a file of this type, right? Okay, so first, I read the program. It's located in my, as you can see, this is my computer, this is my system, but you can put it anywhere as long as you provide the path, and Maple will read it, right? Now it has read it. It is important to load it first because GR Tensor will, as you saw in the text file, it was a defalias declaration. So you have to load it first. Now, here we load GR Tensor. Now it's loaded. And then the following instruction, qload, is telling GR Tensor to look for the metric file the metric file is called FLRW. FLRW.mpl. That's the extension. But then it's already, if your system is well set, then it will load that metric. And so, as you can see, for the FLRW space-time coordinates are x, are r, theta, phi, t, and this is a line element. As you can see, this is a Friedman-Robertson-Walker, a Robertson-Walker metric in spherical coordinates. This is exactly the same one. Thank you very much. This is exactly the...
you can keep with you till this course.
Okay.
Because every day.
Yes, okay. So as you can see, it's the same metric that we saw, but we just change, instead of rectangular coordinates, the spherical coordinates. But otherwise it's the same. Now, first thing we do is to compute and display the Einstein tensor. Yesterday we saw previous tensors like, well, Christoffel symbols are not tensors, but Christoffel symbols, Riemann tensor, Ricci scalar, Ricci squared, all of them. We're really not going to need them. We're now going to work specifically with Einstein's equation. So we generate the Einstein tensor here. It's a two-index tensor. It's mixed. Why? It's always better if you are going to solve the equations to use the mixed form, because the mixed form will give you the tensor itself in the simplest form, and also the stress energy tensor, the energy momentum tensor, will be given exclusively in terms of density, pressure, heat flux, whatever, without metric components. So it's a good piece of advice when you are actually working with Einstein equations. Use the mixed components. Now these are the mixed components for the metric I wrote. They are calculated immediately. Believe me, even with a simple metric, it takes like good 10-15 minutes for an efficient like when I was my first course on general relativity, it was long ago, long time ago. We didn't have access to something like this. So my teacher, who already retired, Michael Ryan, was an American who lived in Mexico, and the first thing first big homework we had was to calculate Einstein equations for spherical symmetric static metrics and for FLRW. It took the whole afternoon to do that. Wow, we were clumsy, somebody more efficient can do it fast, but not as fast as GR Tensor. There are other don't think GR Tensor is the only program around. There are other programs. In fact, I think Mathematica now has a very good program to manipulate tensors. And Maple also has a physics package, which has a sub package called GR or tensors or whatever, and it's also quite good. But it's new for me. I'm still learning it. So maybe the next course we can use this one. But nevertheless, GR Tensor, the problem it was not developed after 2002 or 2003, so this is an inconvenience. But there are other packages. Okay. Now, GR Tensor has two modes. One mode is to compute tensors, and the other one is to define them, because GR Tensor has predefined tensors, curvature tensors, whatever. It's just a long list. I can show you. So there are some help files to see you. There is a help system in GR Tensor, but it has to be accessed not through GR Tensor. I'll show you that later. But
no, I can provide a manual also.
You can also provide a manual.
GR Tensor manual I'll provide.
Yes, okay, excellent. So, but you have to define some tensors, like, for example, here, our objective is to define the stress energy tensor, energy momentum tensor. We want to define the energy momentum tensor. And we are going to use this form rather than the H, because why? Because we have not defined the H. But the metric is already defined, and we need to define first we need to define this whole thing, but we have to start with the pieces, with the parts of it. GAB is already defined. That's not a problem, but we have not defined the force velocity, so we need to define it. Now, the force velocity can be, because it's a vector whose components are understood, are very clear. The components of the force velocity for a Friedmann-Robertson-Walker spacetime are only one is the t component, and the space components are zero because we are in a comoving frame. A comoving frame, the force velocity only has a time component, right? And this is true even in special relativity. So we define it. See, look at the syntagis. The whole sentence here has to come within, enclosed by this type of accents. It's like the French circumflex accent. This defines this whole thing as a string. Now then U, and then the curly brackets, and then the hat. The hat means that the index is going to be up. Okay, and this is like what you would be doing in your notebook by hand. This is a nice thing about GR Tensor, that it mimics. So we define it here. Components assigned for the metric, created definition for U up. Up means index up. But now we calculate let me write here, calculate and display. We calculate and display. That's it. So GR tensor knows this is the 4 velocity. Okay? Next step. Next step, we will need mu. Here I'm using mu instead of rho, but that's trivial. You know, so it's just a change of name. We have to define mu and p. We have to declare them. And this is done right here. Here, we declare these two functions as functions of t. Notice that I have put here a column because I don't want to see the output. The output of this would be saying something that, okay, you have declared these things and so on, blah, 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 blah. It's a long thing. But Maple knows about that. Now we have all the individual parts, and we define this tensor using the following syntax. Syntax is TAB. We're defining a mixed tensor. So the hat here means that index A is up, and absence of hat means that it is down. So we have mu plus p, and then times, this is the ordinary multiplication, but it really means tensor multiplication. It's UA with the index up, UB index down, plus P cross Kronecker delta is predefined also. So it's a predefined tensor. So Kronecker delta AB. See, as you can see, this is what you would be writing in your blackboard. GR tensor is mimicking the syntaxis of our handwriting, which is very nice. So it has already defined it. Now it will compute it and calculate it and display it. So here it is. So in a comoving frame, perfect fluid will always have this diagonal form. So notice that here it is mixed. If it was not mixed, then probably metric functions would appear here. But if it is mixed, we have no metric functions, only the pressure and the density. Notice that the density here appears with a minus sign. Okay? Now, next thing we want to define is the balance equation. Okay? The energy momentum balance here is a divergence. So it has one free index. So it's really a vector. See? And we are going to look how Maple works with the covariant derivative. It's the index A, index B, and then semicolon B. That's a notation for it, and this is going to be 0. Now we have to give a name to this object, which is strictly speaking a vector because it has one free index. So we call it J, and this is the definition. So it's exactly as you would be writing in your notebook. Now it's defined, and we calculate and display. See, what we get is a vector having only the time component. This thing has to be 0. This is the condition of energy and momentum balance. Notice that for an FLRW space-time, the momentum balance is trivially 0 because there are no gradients, no special gradients, because everything depends on time. All spatial derivatives of quantities are 0. So the only thing you will have is the energy balance condition. Okay. Now, here's some manipulation you can do using GR map. The syntaxis is very simple. GR map, on acting on the above calculated object, applying the instruction collect in terms of these quantities, it will collect on powers of these quantities and will factor. Okay, let's do that. See, and it will modify this tensor to place it in this form. Instead of having it like this, now we have it like this. Okay. Don't worry if you cannot do these manipulations, because you can do them later also, just to show you that it's possible to do them. Now, once we have the Einstein tensor and the energy momentum tensor, we can write the field equations in this way. We can define them as an equation. Notice that this is an assignment and this is merely an equal sign. It's very different. Don't never confuse them because they are very different. So we are going to define a tensor that I'm going to call EE, Einstein equations, mixed tensor, and the tensor will be this equation, right? These Einstein equations. And after defining it, we're going to compute it and display it. Here. Notice that this is the component 1, 1, the 2, 2, 3, 3, and 4, 4. Notice how these are identical. This means that Einstein equations reduce to two ordinary differential equations. Ordinary differential equations because A is strictly a function of time, right? So now we have Einstein equations. Okay, so what we can do, we can, for example, identify components. For example, we know that the J up that we computed only has a time component, so we can extract it and give it a name, right? And the same thing we will do with the non-trivial Einstein equations. So we can do this. We can do this, but I will show you now something that is much more efficient than doing this. You can always do this. See, here you have J4 is this object. It's now isolated because you don't need the zeros. You only need this one, right? And then the same thing we do for Einstein equations, right? These are the three equations that we need to consider. Two of them are, they're not really three independent equations. Why? Because if these two equations are satisfied, this is trivially satisfied. Any combination of two of these equations is sufficient to guarantee that the next one is identically satisfied. So they're not really three independent, but two independent. One of them is an integrability condition of the others. This is an integrability condition of these two. Anyway, we can do this, but there is a disadvantage of doing this. The advantage is that you have them in a compact form, but the disadvantage is that this, the GR component, this is still a GR tensor object. And sometimes Maple will have problems with manipulating. It's strictly speaking, not a pure Maple object, right? So it's better to do the other, something that I will show you right now. You remember yesterday I showed you that Maple can generate arrays and vectors, right? So what we're going to do is, let me write here the comment. See, no, not here. Let me write it here. My comment. Note. See, it is always better to generate pure Maple objects from GRT objects, right? And namely arrays. So what we're going to do, I add here a few lines, and what we're going to do is the Einstein equations. I'm going to define this thing will be an array. And the array will be formed by the tensor that we have already defined. Okay. But what's the advantage is that this is a Maple object. We can really Ah, yes, 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 yes. Okay. So, here, figure 4. Okay. Right? So, now, as you notice, Maple has, we have done a substitution. This syntax is the composite. As I told you, Maple treats instructions as functions. This is the way you compose functions in Maple. It's a composition of evaluate over substitute. And what is substituting? P equals W mu. Since W I have not put in the alias, Maple takes W as a constant. Of course, it would be nice to tell Maple that it's a real constant, but we can do that later. Now, it has already replaced P by W mu. And so now, what we're going to do is isolate mu of t. And it's very simple. We say mu of t divided by mu is expand. First, it's going to solve. Maybe I should fragment this into instructions. Let me fragment this into instructions so that you understand what I did. First, we solve above the above thing. We solve it for, let's say, mu of t equals. First thing we do is we solve for mu, right? What we did is that we solved the above equation for mu of t, right? And then the next thing is left-hand side. We say left-hand side of the above thing equals divided by mu equals expand the above thing divided by mu. So, sorry, H, right-hand side. Okay, so we do it again. Okay, so this is the differential equation that we have to solve. See, this is a differential equation that we have to solve. So let's solve it. Let's tell Maple to solve it for mu. And it's readily solved, right? Here, you see. This is a solution with integration constant. So what's the integration constant we're going to put? It's going because A is dimensionless. This is dimensionless as well. So the whole thing has to have the dimensions of mu. Therefore, it has to be an initial value of mu, an initial density. So we tell Maple to substitute the integration constant by mu0, right? And this is going to be the equation for mu. So as you see, now we have mu as a function of the scale factor, right? Which I showed you in the lectures that it was the first thing to do. Now, once we have this, we substitute this form of mu in the 4-4 equation. And it's this thing, okay? Now, what we want to do is to isolate this derivative. So to isolate this derivative, right, we take the negative of the left-hand side, multiply it times a squared to remove a squared, and then divide everything by 3. If we do all these operations, we isolate this thing. But if we do them in the left-hand side, we have to do them in the right-hand side as well. So we have now this. And notice that here we have a squared and a to all these powers. So we simplify with option symbolic to group all these exponents. And then it leads to the Friedman equation. So this is our Friedman equation. Yeah, well, it would be nice to be able to to pass the K0 on the other side, but anyway, that's okay. Now to solve it, let's consider the flat case, and it would be useful to make assumptions on W. Say that W is a real constant, right? So first thing we do is let's define Friedman equation 0 That's the flat case. This is the flat case, right? Now, here we make an assumption on W. We're going to tell Maple that W is a real constant that can take values from -1 to 1. Okay? We make this assumption, right? And now we should be able to solve this thing. Well, Maple should be able to solve it. That's a very simple equation. That's still GR tensor interfering. It should be.
What you do, you cut that equation and this one. Just cut that. Cut it.
No, but you have to do it in another
Maybe
portion.
for now you can just cut and put.
Yes. Okay. So. Yeah. No. What? Okay.
Just
This is a glitch.
Yeah, that's right.
This is a glitch.
Yeah.
No, but you have to do it in a separate worksheet.
Now here also I think.
You have to do it in a separate worksheet.
Alright, just right.
That's a pity. That's a real annoying thing. It's still interfering. I don't know. It's okay. Okay. It's a very simple equation, so Maple really has to do it very quickly, but because there is interference with GR tensor, for some reason, I've already checked because Maple has a possibility to look at the kernel while it is working. And it's lapses because
It
it's
is
still
actually
like
only
that.
in Maple 15, not in 13.
Yes, that's true. From Maple 13 below was no problem. But now Maple, if you are working with GR tensor, it takes all these objects as parts of vectors and arrays and so on, and it's very annoying. But so the point is that you can solve this equation. You can solve this equation, and let me just pass it here. Okay. Where I'm going to cheat here. Sorry, I'm going to cheat here, but that's okay. Let's call this thing A. Okay. So this is the solution now, and of course we can simplify. We can simplify this symbolic. Okay, simplify symbolic, and then we can substitute. The integration constant is the value of A for T0. We can take that to be 0 because A is a scale factor. It has to be 0 at time equals 0. So substitute this constant in above, and okay, here this is going to be A. Now we substitute this equation in our, and we factor all these things, and then this is as you can see, there is a problem here in Maple when working with these things, and I purposely wanted to show you, because sometimes why I had to do this, why I had to cheat Maple, to take out of the worksheet in another worksheet and solve a very simple equation. Why Maple was unable to solve it in the original one? because newer versions of Maple are not well adapted to an old program that has not been developed for more than 10 years. See, that's a problem. Anyway, not wasting more time on this. And here there is a comment. Obviously, this is the solution. This is what you would get if you do it by hand. You would get it immediately. So what we see is it's complicated to force Maple to write it in a simple way. But this is the solution. Okay? What we see is that the solution of the Friedman-Robertson-Walker equation with a simple equation of state is that A is a power law. What happens if W is 0? W is 0, W equals 0 is dust. If W equals 0, then the solution will be A to the power of 2/3. And we know that the solution would be T to the 2/3. And this is a known solution for Friedman-Robertson-Walker dust. Okay? Well, now let me go to the other to another worksheet that is also on Friedman-Robertson-Walker models. This is the number 4. Did I send you the number 4? No, only the number 2 and 3. The number 4, no? Okay. So this is more ambitious. This is more ambitious. Why? Here we're going to get the Friedman-Robertson-Walker equations for a fluid and also for a scalar field. Scalar field can also be written as a fluid. I'll show you how you can define the density and pressure of the scalar field. Every source that you can imagine can be written mathematically as a fluid. See, in fact, fluid is essentially a mathematical concept. That as long as you have a 4-velocity field, you can always define the fluid. And the scalar fields are very useful. People use them to model dark energy. They're used for inflation. So it's very, very handy to be able to work with the scalar field. Now, the same things, I'm going to go faster now because I think you are now experts in GR tensor. So we start, we load GR tensor, we load the Falias, and then we load this. This is the Friedman-Robertson-Walker metric in another coordinates. In these coordinates, we have a function f. The curvature of the space-like slices is given now by a function f. See, it's spherical coordinates, and if f is r, then it's spatially flat, but can be sine or hyperbolic sine. Sine is positive, and hyperbolic sine is negative curvature. Okay, so but now let's also look at the metric file. So it's also illustrative. This is the file number 3, RW3, and okay. Now notice that we are now declaring A to be a function of t and small f to be a function of r. Now this small f can be r, can be sine of r, and can be hyperbolic sine of r. Therefore, this f is satisfying these equations. It's satisfying these equations. See? It's f prime double is minus, okay, and f prime you can check that the solution of this system okay this information. Okay, but this is the file. Why I'm doing this? Because I want you to see there are several spatial coordinates for the FLRW metric. I want to see that you can work in all of them. It's irrespective. Whatever spatial coordinates you use, the results are going to be the same. Okay? So we have loaded now the FLRW metric. Now, here we write these constraints. Because we know that the function f has to satisfy the second derivative constraint and the first derivative constraint. And we will input this. Okay, I'll show you how we will put this inside. This is important because when you work with metrics, it's always better at the top level to put the most simple form, right? The simplest form of the metric. And then to be placing constraints and substitutions along the way. Not the opposite. If you put everything substituted on top, you get horrible outputs, right? Okay, so first we compute define and compute the four velocity, right? Now we declare density and pressure, and now this is what we did also in the last one. We define the energy momentum tensor of the fluid. See, TF is T of the fluid, right? You have the liberty of using any name for the tensors you are defining, provided it does not clash with previously defined tensors, and be careful that it doesn't clash with the indices. Okay? Yeah, I'm using as indices A, B, and C, and so on. So I can't use a small lowercase letter because it will be a conflict, see? So the alphabet is very generous. We can use millions of combinations of names. So use them in order to avoid conflict. And this is, we calculate and define it. This is what we did. And then this will be the J, the conserved current for the fluid. We calculate this and display it, right? This is what we did in the last. Now, the Einstein equations for the fluid, I'm now going to write them, not as equations, but see, this minus this equals 0, something to be equal to 0. It's the same thing, right? Here, and then this is displayed. Here I calculate first. See, when Maple calculates things, it calculates all the intermediary, all this. See, Maple to calculate this first did the Riemann, the Ricci tensor, then the Ricci scalar, then the Einstein tensor. See, it tells you all the intermediate steps that it did. Okay. Now, here we display it, and these are the. Okay. Now here we have the function f, because we have not said anything about f. We have the constraints, but we have to substitute these constraints. See? And then it will simplify, it will eliminate these double derivatives and single derivatives. How we do that? We have to substitute now these forms. And so we have to substitute these derivatives. So first, and we do it global. So we use GRMAP. See? GRMAP, and always, when you have to substitute derivatives, always start with the highest derivative. Why? Because if you substitute the first derivative, then it will give you back second derivatives, right? So better substitute all second derivatives, and what is left is only first derivatives, and then you substitute first derivatives, okay? This is also another golden rule substitution. So we substitute first the second derivatives. Notice that no more second derivatives of f appear, only first derivatives, and the function itself, okay? Now, we substitute also, now no derivatives of f appear, only f itself, but f itself will cancel. Notice how f itself will cancel, right? And to do that, we expand, we perform an expansion globally, and this is the This is the Einstein equations that we have. Of course, yeah, we have to display that. Okay. These are Einstein equations. No more F, we got rid of F. Which show, see, if we had used another form of the FLRW metric, we have obtained the same thing. See, this means that the function F is a coordinate thing. It's not, it's a one way. Why to use some coordinates and not another ones? It's coordinates are our slaves. You have a slave that is very good to make coffee. You have another slave who is very good to be like this with a fan. So, which slave are you going to call? If you want to have coffee, you call one. If you want to, you feel hot, you call the other one. So that's coordinates are like that. It's up to your convenience to use one coordinate or the other. Okay? So now we have. Let me. Yeah. Okay. It doesn't matter. We can use this one. And you already know that you can either declare the array and take a component of it, or extract the component. Here we're making EEF is the array for the Einstein equations for the fluid. And so these are the equations that we are going to use for the fluid. Okay? Now, we do the same thing. We isolate the equation for mu, and this is one equation we have. And then we do the same thing for E44. Maple doesn't like it, but it will do it. You just ignore that setback. And then we do some manipulations, and we have here the Friedman equation written in this form. We are going to call this thing will be h squared, and this is a Friedman equation. And now we're going to generate the Ricciardo equation. So first, we generate, we solve and expand the equation for ATT, and then we're going to substitute the equation before, and we factor everything, and this is the Ricciardo equation. Okay? Very simple. As these equations that I've shown you in the, remember these equations? The second derivative. This equation tells you if I've set cosmological constant you can always, by redefining P and mu, you can obtain a cosmological constant.
The Lecture-3 equation also is a function in GR tensor.
Yes, that's true. That's true.
Yeah, you can directly also do.
Yes. But yeah, that's true. It will generate the Ricciardo equation. But it will I don't know if it generates it in terms of the kinematic parameters or the metric. I think it generates it in terms of kinematic parameters, which we will see that also along the course. But so these are the equations that we have. Okay? These equations, I've shown them to you in the course. So now we've derived them. Okay? Now let's go to the scalar field. Yes, before.
Yeah, in terms of h.
We're going to substitute instead of why do that? Why we should be bothered by introducing h? This thing is h squared. Here we have an h, and this will be a first derivative of the h. So why we do that? To reduce the order of the equations. That system is a second order. If we introduce this definition, we transform this system into a first order system. Why? Because numerically it's always better to work with first order systems. Okay? So we do that. We introduce, first we declare h to be a function of t, and this will enable us to substitute whenever we see a of t. Maple will put this, and as you will see, it will cancel the a in the denominator, right? So let's start. First, we obtain this equation. This equation now is first order, right? It was already first order, but it is now involving only one derivative that is first order. Then we do the same thing here. Now the Friedman equation is no longer an equation, but it's an algebraic constraint, right? So that's nice, because we don't have to, it's always better to do algebraic solving than differential solving, okay? Now this is going to be H2. Now we do the same thing with the other equation, and we isolate H, and then we collect terms, and we substitute again A of t, and this is our equation. So we have now two dynamical first order equations, right? And an algebraic constraint, right? And this is what we can do, the most efficient way to do numerical work with it. Because you do have a system of first order equations. All the variables have physical interpretation, and this is now an algebraic constraint, okay? Now, we're not finished. We're not finished. We're going to construct a dynamical system, okay? These variables are nice, but we can use other variables that are even nicer, because they are related to observational parameters, the omegas. See, you remember I told you yesterday, what's the problem using density? Well, because cosmic density is very small. Cosmic density, 10 to the minus 24, 27 grams per. If you are doing numerics, you have to give numbers. And if your density in present cosmic time is 10 to the minus 27, can you imagine putting into the computer 10 to the minus 27? Computer will be very angry with you. Computers want numbers that are, let's say, 10 to the minus 2, or maybe, okay, so also if you take your density very close to the Big Bang, then instead of being 10 to the minus, will be 10 to the 27. Computers also don't like numbers so big. So why we do that? Because if we divide the density by another reference density, which is the critical density, remember, this I'm going to emphasize again, because this has to be very, very well understood, extremely well understood. See, omega of matter is going to be 8 pi g over c fourth times density. Okay? Now, we know that g is I think is 6.8 or 6.67. Okay. Times 10 to the minus. Sorry?
11.
But in what? In centimeters or grams?
SI unit.
Meter.
Okay, it's so what? 11? No, es a menos 8. I think it's minus 8. It is centimeter square cube times gram second square, right? Okay. And then C, of course, is 3 times 10 to the 10 centimeters per second. Okay, we substitute all this, and then we get numerical values, right? But this quantity, here, sorry, h squared, and a 3 here. That's it. Okay. Now, units of h are 1 over centimeter. Okay. Now, this quantity here, this quantity here has units of density, right? This is a density. So this quantity here has to have units of inverse of density, right? And in fact, we call, if we are, let's compute this, let's make it in present cosmic time, right? Okay. So this quantity, H0 squared, H pi G, this is a density. It's the inverse of the other one, right? You agree this is a density? Yes? Now, this is a density, but it's a very nice density. Why? Because it has one fundamental constant, another fundamental constant, and something that is observable, right? This is H, this is the rate of how galaxies recede from us, right? Now we substitute values, say H0 is about 70 kilometers per second per megaparsec. Now I didn't say megabytes, megaparsecs, okay? So we compute this, and then this turns to be of the order 10 to the minus, I think, minus 29 grams. Well, it's really, we can always transform from ergs to grams by dividing by c squared. Okay. Right. And the observed density, or cosmic density by number counting, is of the same order of magnitude. Therefore, if we divide this, which is very small, by this, which is very small, what we get? A decent number that computers like. Okay? So this is the reason why of using omega factors in cosmology, right? Now, for this same reason, we're going to transform this system in terms of omega factors, because we can do numerics with that. We deal with decent numbers. We don't have to do 10 to the minus 29, right? We do numbers of order 1, okay? We know, for example, that omega of cosmic, of large-scale dark matter is around 0.3, 0.2. It's nicer to work with 0.2, 0.3 than 10 to the minus 29, okay? So it's important. Now, we are going to introduce omega mu and omega p. Why omega pressure? What are the units of pressure? Divide, pressure is force divided by area. You transform this, this is the same as an energy density, it's ergs per cubic centimeter, right? So pressure is an energy density, and therefore we divide by an energy density. Okay? So we do all this transformation. So what are we going to do is the following. See? The left-hand side, we're going to divide by h cubed. See? Okay? And then the left-hand side, see, this is just to show you how the equations will look like. Well, okay. This is just to show you that see here we have mu over h squared, p over h squared, and here the same. This is to show you, this will be related to the time derivative of the omega factor. But now, let's introduce, see, since we're using a very simple, we can use a very simple equation of state. P equals W mu. Therefore, the omega of P will be simply W times the omega of mu, right? So we only have to define one omega, which is the omega of mu. And here we first declare it, and then we state the equation of state, and then this is omega, and now we solve for mu. We express mu as a function of omega, and this is the thing that we are going to substitute. We're going to substitute this. Instead of mu, we're going to substitute omega, and then we will input omega. Now, let's do the substitution first in the equation H2, and then we eliminate this quantity here. We eliminate from yes, we're going to eliminate this thing here, okay, and we factor it, and this is going to be the equation that we're going to call this equation AH. Notice that this equation is merely defining curvature in terms of omega. What you can see here is that if omega, and this is the omega of matter, is greater than 1 or smaller than 1, curvature will be positive or negative or 0. Okay? Now, we continue substituting. Okay, now we need an equation for the time derivative of omega. Okay? So what we do is substitute first the equation of state in the equation that we already had for mu. And now we substitute instead of mu to get omega, and here we have derivatives of omega, and now we isolate the derivative of omega, and then we expand everything, and now we have to substitute for the equation of ht, and then we substitute the equation of state, and we factor everything, and now we divide everything by h, and this is the equation for omega. See, we're just changing. You can do all this by hand also. Don't think it's very complicated. What we're doing is substituting instead of an equation for mu, now we have an equation for omega, because omega we can interpret as a ratio of densities. Okay? Now, this is we're going to call equation for omega t. Now, let's get the equation for ht. This is ht. We substitute the equation of state.
Excuse me. That omega is present time density, no? In equation number 47, that omega is omega naught.
No.
Present time or?
No. Omega is not omega. Omega is changing. If it was omega naught, it would be a constant, and its derivative would be 0.
Okay, that omega t is derivative.
Eh?
Omega t on the left hand side, that is derivative with respect to t.
Yes.
Okay.
Yes. A sub-index is
Yeah.
derivative. Okay. No. Here I used omega 0 to illustrate to you why it is better to work with something, because you want to integrate these equations from, let's say, the Big Bang to present day. So in present day, you don't want this quantity. You don't want to work with quantities that are 10 to the minus 29, right? This is the purpose, but that doesn't mean that omega is a constant. I use that example to.
I was confused with the notation. I thought that omega t is time variable in that.
No. Omega is a function of time. It's this definition, but just remove the zeros. Yeah.
Yes.
Okay. No. You can see it. The way I define it is an algebraic function. It's a very simple algebraic function of mu and h. So it has to be a function itself. Okay. So now we substitute instead of mu to get the omegas, and then we divide everything by h squared and expand, and then collect terms, and so this will be the equation for h. See? So h.
T, we have T here. Half an hour now.
In a few minutes. It's we're about to finish. Okay. Now this is the result, right? And then the nice thing, we have two equations here, this one and this one. And the nice thing is that, notice that in these equations, there is no h here, and there is no h here. And this is very nice because we can define a new time parameter, which will be the derivative divided by h. This is like a new time parameter. And the advantage for numerical work is that we are able to decouple this equation from this one. And this is very interesting because these are the two equations that we have to work with. See, this one and this one. See, we have this. These equations are our dynamical system. In fact, we have here a one-dimensional dynamical system, essentially.
Tau
And
is log
you-
in here.
Sorry?
Tau is log of A.
No, no,
Yeah, tau is related to log of A. Yeah, that's called also logarithmic time. But the point is that this is the real dynamical equation. This is a one-dimensional dynamical system. You can immediately identify the critical points. One critical point is omega equals 1. And this is an attractor, a past attractor. And another critical point is W equals minus 1/3, which is also the point where the expansion becomes either accelerated or decelerated. But it's a one-dimensional dynamical system because it's an extremely simple. We'll see that the scalar field leads to a three-dimensional dynamical system. Now, why this equation is not necessary? Because this equation essentially is a definition of the time parameter, and this is simply an algebraic constraint. So here, by using these variables for the Friedman-Robertson-Walker model with a perfect fluid and a simple equation of state, we obtain a very simple dynamical system. See? We'll see that the scalar field is more complicated. Okay, so let's have tea and we'll continue. See, it has minus dt squared plus some element like this, some three-dimensional metric. Now the three-dimensional metric, let's call it ds squared 3. Let's call it ds squared 3. This part can have different forms. This is in Cartesian coordinates. This is in Cartesian coordinates, right? Now, you can easily transform this to spherical, simple spherical coordinates. It will be okay, right? But this is a simple transformation. This you take flat coordinates, you put spherical coordinates, and it's transformed like this. The transformations are x equals sine of theta, cos of phi times r, y equals sine of theta, sine phi r, z equals cos of theta r, right? It's very simple. Now, the ones I use now are not related in such a simple way to this one. The ones I used in this worksheet were in fact, let me use another letter. Cross. is not this. These are sort of spherical coordinates, but the transformation relating them to Cartesian is more complicated than this one, right? And then there is still another one that is also very useful, which has this form. In fact, I'm using different letters so that you don't get confused. This is still another one. But the relation between these two and Cartesian is more complicated, right? So just have to be careful. There is always coordinate transformations that are well defined and are well behaved that transform one to the other. However, once you do the tensor calculations, the Einstein tensor and everything, they all lead to the same form. And this is the test, because you can always introduce funny coordinates, and you will get funny components of the metric. But once you calculate tensors and you use tensor equations, you get the same thing. See? This is tricky, but it's important. Now, this is one question. Another question somebody asked me is how you dimensionalize, how you make an equation dimensionless. For example, suppose we have this Friedman equation. Okay, have this equation. Now here, this is a very compact notation. I'm removing fundamental constants and so on. But to see the dimensions, if you have problems with the dimensions, then invite back all this. You kicked out C and you kicked out G and all these constants. So invite them back. Say, okay, sorry, come back, I need you. So we write the whole thing with full dimensions. And then you have to realize that this fellow is really, right? Because we want the coordinates to have similar dimensions. Now, that's another important point you have to bear in mind. What is the dimension of theta? 1, 0, dimension. It's an angle. So, if we use as coordinates, suppose our coordinates are these, CT. There's no problem with R and CT because they have dimensions of length. But then say, oh, why do you mix coordinates? You are crazy. Doesn't matter. The important thing is that this fellow here, coordinates are slaves. It can be dimensionless, it can be dimensional, doesn't matter. What is important is that this thing, which is in itself a contraction, this is GAB, DXA, DXB. This is a contraction. This is a scalar invariant. This thing has to have dimensions of square centimeter. See? So if you have a coordinate, for example here, all this thing is dimensionless. But notice that it's multiplied times a square length. So this thing will have dimensions of square length together with this one. This is dimensionless. But how is this dimensionless? Because K0 is really a curvature, so it has these dimensions. Okay? K0 is not, we say it's 1, but it's really 1 divided by a characteristic length. Now, how do we make this thing dimension? So first, what we have here, what is the dimension of this? The dimension of this is 1 over square centimeters. Now this is going to be, okay, it's centimeter cube, gram, second squared. This is G, okay? Now, C fourth, centimeter fourth, second fourth. Now this is an energy density, so it's ergs divided by centimeter.
So into a square.
What?
So multiplied by a square. This is rho a square.
Ah, yes. But it's dimensionless. Okay. But A is dimensionless, right? It's a scale fact, right? So the dimensions are correct. So if you change this, cancel these things, and then these things will cancel, and this thing will cancel. So the dimensions are correct. So how do we make this thing dimensionless? We have to multiply or divide on both sides by the appropriate thing. Now, what is an appropriate thing here? H squared. So what we do is divide, if we have this, squared, we divide by H squared, then this is dimensional. And then what we do is we take this object here and call it omega. Because, again, as I was telling you, this thing here, this has units of energy density. And this we call it the critical density. This is how you make things dimensionless, okay? Just write the dimensional form. You have to divide, multiply, or make substitutions. There is no general rule. It depends, and this is why physics is difficult, because it depends on your skill to recognize which are the best variables, okay? So I think this is a minor thing, but it's important. And it's also very important for practical purposes. When you are doing any calculation, for example, people working in inflation, quantum gravity, or particle physics, they use other systems of units. They don't like centimeters, megaparsecs, and so on. Obviously, you're not going to use megaparsecs for quantum gravity. So they use the Planck length. They take the Planck constant and make all sorts of juggling with the Planck constant, multiplying times c, dividing by g, and so on, to get lengths and to get energies and so on. But then it's the same process. It's just with different units, because they work with very small quantities, and we work with very big quantities. Okay. Well, now let's go back here to the scalar field. So we see this is an interesting dynamical system, because you can show that this is a past attractor and this is a saddle. What does it mean? If this is a past attractor, it means that all Friedman-Robertson-Walker models in the past had omega equals 1. And this has very strong physical implications, because as we go back in observations to the past, we see that it is natural for Friedman-Robertson-Walker models to become spatially flat. See? Now this is also it's an unstable attractor. It means that very slight deviations from omega 1 will propagate into very large difference among the models. See? And but you can obtain this immediately just from looking at this dynamical system. See? Have you been, are you familiar with this? With what I'm saying? Yes? Have you heard of it?
Why you said it is a past attractor? It is a critical point. Right?
Yeah, these are
First
critical
derivative
points.
is 0. It's a critical. Why you said it's a past attractor?
Because critical point can be saddle, can be an attractor, can be all sorts of things.
The
And
past in meaning past meaning
in the
backwards
past,
in time.
backwards in time, yes.
Like why you said?
Because what you do is you look at the typical phase space analysis. You look at the critical points, then you linearize the equations and look at the eigenvalues of the linearized equation. So the linearized equation is a linear equation, and then you look at the eigenvalues, and if the eigenvalues are both real negatives, then it's a past attractor. Okay. This is and that means that all Friedman-Robertson-Walker models of this type, if you look at them very far into the past, very far into the past, and remember we're using a logarithmic time. See, we are using this time, this tau is 1 over h. It's really the integral of h. So it's essentially the logarithm of the scale factor. And if the scale factor goes to 0, its logarithm goes to minus infinity. So if you take time going to minus infinity, you see that all the models approach omega. The omega is going to evolve for these models, right? But in the past, all of them go to omega equals 1. See? Again, in the blackboard, see, let me show you what would happen here. What happens here is that you take omega for all these models. See, here we're plotting omega as a function. Omega cannot be negative. But here is omega equals 1. Divide tau. Okay? Now, tau going to minus infinity is the same as a going to 0. So what you see is this. All the models are converging here. See? They are converging here. Right? This is the mean. That means that in whatever value W might have, whatever value, originally all these models began with omega tending to 1. Okay? So this means that if in the past, this is a far past, very slight minute deviations from omega 1 will give you very different evolutions in the future. Okay? Is that understood? You get this from that simple equation. Okay? See, it doesn't matter. Here we're plotting for different W's. Doesn't matter. Suppose you take W equals 1/3, which is radiation, or 0, which is dust. Doesn't matter. For every W, you will obtain models of this type for different initial conditions. You set your initial conditions here. This would be your omega initial, and very minute deviations from omega 1. All these models have these trajectories in phase space. Okay? So lights went off. Okay. Well, let's now go see the scalar field. Was this understood? Yeah. It comes directly from, if you solve numerically this system, you will get curves of this type. But you don't have to solve it, because already, qualitatively, you know that this is a past attractor by doing the phase space analysis. This is almost a trivial dynamical system. It's one-dimensional. Okay? Now, let's go to the scalar field. Okay. Scalar field. First of all, a scalar field, the energy momentum tensor of a scalar field is, let me see if I can, plus, you might get this thing.
I think you need to write bit bigger,
Bigger?
because this from here,
Okay.
you can rub. Yeah.
Let me write. Maybe I have a sign wrong or whatever, but okay. This is the energy momentum tensor for a scalar field. This is the D'Alembertian operator. Okay. Now, for Friedman, Robertson, Walker, this will turn to be a fluid where the density will have this form. And the pressure will have this form. Okay. But it can be treated as a fluid with this density and this pressure. Now, you can see how if this is very simple, essentially because these two gradients morph into this thing here, because there are only time derivatives. But if you have space derivatives, then this can be quite nasty. These are extremely nonlinear, complicated stress energy tensors. Okay, so first we declare phi. Phi will be the scalar field, and V of phi is the potential of the scalar field. Okay? But we will declare them both. Of course, V is a function of phi, but we will declare it as a function of time. Okay? So we first declare the field and its potential. Just to show you what happens when you do this, when you do a declaration. When you do a declaration, Maple is reminding you all your previous declarations, right? Up to the third order derivative, okay? Now, let's define first the gradient of the scalar field, because we need to define the following components. We need to define this object. This is a gradient, say this object, and then we also have to define the, well, for Friedman, Robertson, Walker is basically this one what we need to define. Okay, this is the gradient of the scalar field, which has only the time component, and it's a time derivative. Okay. Now we calculate this, calculate and display. See, this is the gradient. Now, here is the definition that I just wrote in the blackboard. I wrote it with a minus sign here. Okay. So this is the definition of the energy momentum tensor of the scalar field. Right? And it is calculated. The scalar field for Friedman, Robertson, Walker, it's a fluid with this density. This is negative of the density, and this is the pressure, right? So that's it. That's a scale. Now we work the field equations for this source. Okay, so let's look at the divergence of the energy momentum tensor, as we have done before. And we calculate this. And here you see the Klein-Gordon equation. See? The Klein-Gordon equation, notice that, well, this thing, essentially you divide everything by phi dot, and then if you divide this by phi dot, then it's going to be the derivative of V with respect to phi. So the Klein-Gordon equation is right there. Now let's write the field equations, the Einstein equations. Einstein equations are calculate and display. We don't need this one. Okay. This is the Einstein field equations for scalar field. Now we eliminate the function small f and its derivatives. The same as we did before, right? We use these constraints and we substitute them one by one, and we normalize, we display the whole thing. So this is these are the field equations As you can see, the left-hand side is the same, but the right-hand side is now different. Okay? We identify this component, and we transform into an array, and we modify this one. We modify by dividing everything by phi of t. We substitute v equals v of phi, and so this is the Klein-Gordon equation. You can see this is the Klein-Gordon equation. Okay. So we define it as Kg, Klein-Gordon equation, and these are the field equations, right? So these are our equations. These three, and of course we can always substitute. For example, instead of this one, we can use this one and work with these two equations, just the same as we did with the fluid. With the fluid with a simple equation of state. So to get a first order system, we do the same as we did before. We call this, we will use a function psi, and this function psi, see, why we do that? Because notice that there is no phi, only derivative of phi, first and second derivative of phi, right? So instead, we are going to define this variable to eliminate first derivatives of phi. So second derivatives of phi will be first derivative of chi. Okay? That correct? Please see, if you don't understand, you get lost, whatever, interrupt me. Okay? Would rather be interrupted than start talking to flat faces that don't understand anything. Okay? So do interrupt if you don't understand. Okay? Now, we do these substitutions in the Klein-Gordon equation, and the Klein-Gordon equation is now a first-order equation, right? So only first derivatives appearing there. Now we substitute this in the equation 4,4, and the equation 4,4 is Friedman equation, becomes again an algebraic constraint. No derivatives here, only an algebraic constraint. Okay? Now, we do the same thing with the 1,1, with the Raychaudhuri equation. We do some modifications here, and this is the equation we have. Now we isolate the derivatives of chi and h, and do more. These are just algebraic manipulations, but here are the equations that we have to solve. This is the system that we have to work with now. Notice that. Well, we're going to introduce the omegas and everything, but notice that this is an algebraic constraint. This is an equation, a first order equation, and this is a second. The only thing that is the only thing that is spoiling the pleasure is this thing. We have A here, so we need an equation for A as well, which will be the definition of the Hubble factor. But anyway, this is a first order equation. However, we can eliminate K0 from the first equation and substitute here.
What is the symbol that on second equation, right?
Here?
No,
This?
no, Xi. Acha, that is
Chi. Chi is the first derivative of phi.
phi. Okay.
Phi dot is chi.
Okay.
In order not to reduce the system from